Hello everyone, my name is Radhika Gupta and this is the video of my homework questions. In first question, we have to prove that probability of A union B given C is greater than or equal to 1 minus probability of A union B union C upon probability of C. In order to prove, I've assumed that probability of A union B given C is less than 1 minus probability of union of all three, that is A union B union C upon probability of C. And now I've assumed cases after solving left hand side and RHS, that is right hand side, separately. So on solving left hand side and right hand side separately, I get, first of all I'm solving right hand side. Probability of A union B union C upon probability of C, that is 1 minus, is equal to P of C minus P of A minus P of B minus P of C plus P of A intersection B plus P of A intersection C plus P of B intersection C minus P of A intersection B intersection C whole upon P of C, which eventually gives me minus of probability of A minus probability of B plus probability of A intersection B plus probability of B intersection C plus probability of A intersection C minus probability of A intersection B intersection, A intersection B intersection C whole upon probability of C. This is my right hand side after solving. And on solving my left hand side, I'm getting probability of A union B intersection C upon probability of C using conditional probability. Now I've assumed cases. My first case is represented by the Venn diagram as given here. Set A, set B and set C. So on using this Venn diagram, when I substitute values in RHS, I find that RHS is coming out to be less than 0. And since we know that probability of an event can never be less than 0, hence this case is not possible. Now my second case is that I'm assuming that B and C are two mutually exclusive cases which are sets which are subset of set A. Now using this Venn diagram, when I solve right hand side, I find minus the probability of A minus probability of B. Now since B is a subset of A, therefore probability of A intersection B gives us probability of B plus probability of B intersection C is equals to 0, as B and C are mutually exclusive sets. Probability of C intersection A is equal to probability of C, and probability of A intersection B intersection C is again 0 whole upon probability of C. Now since C is a subset of A, therefore this entire right hand side is coming out to be negative, and again since the probability can never be 0, therefore this case is also not possible. Now my case 3 is that I've taken set A and the set B and C are two subsets of A. Now using this Venn diagram, I started solving RHS. I got minus P of A minus P of B plus P A intersection B again gave me plus P of B. Similarly, plus P of B intersection C plus P of C intersection A is again equals to P of C, and minus of P A intersection B intersection C is equal to minus of probability of B intersection C whole upon probability of C. Now I can cancel these two terms, and similarly I can cancel these two terms. Yet again we found that this probability is coming out to be negative, and since probability can never be less than 0, therefore the case is not possible. I'm taking yet another case, case 4, where I have taken a set A. B is a subset of A such that C, another set, is a subset of B. Now using this Venn diagram, I started solving RHS. So I got minus P of A minus P of B plus P A intersection B gave me P of B plus P B intersection C is equal to P of C plus P C intersection A gave me P of C minus of P A intersection B intersection C gave me minus of P of C whole upon P of C. This term is cancelled by this, and this term is cancelled by this. Yet again this probability is coming out to be negative, and since probability can never be negative, therefore this case is also not possible. So using all these cases and similarly using other cases as well, we came to the conclusion that the assumption that we made earlier, that is probability of A union B given C is less than 1 minus probability of A union B union C upon probability of C is not possible. Hence, by method of contradiction, we came to the conclusion that probability of A union B given C is greater than or equal to 1 minus probability of A union B union C upon probability of C. Hence, proved. So we have proved the first question, and now starting with the second question, we know that the second question we need to prove that probability of A given B plus probability of A bar given B bar is equal to 1, provided that is given to us is that A and B are independent. So in order to prove this, first of all, I wrote what we need to prove in a simpler manner, that is by using the condition probability formula. We know that probability of A given B is given by probability of A intersection B upon probability of B, and similarly probability of A bar given B bar is equals to probability of A bar intersection B bar upon probability of B bar. Now since we are given that A and B are two independent events, therefore here probability of A intersection B will be equal to probability of A multiplied by probability of B. Using this, we have P of A in A given B is equal to probability of A multiplied by probability of B upon probability of B is equal to probability of A. This is my first result. Now, we know that probability of A bar intersection B bar is equal to probability of A union B whole bar. That is, it is equal to 1 minus probability of A union B. So I can write it as 1 minus probability of A minus of probability of B plus probability of A intersection B, but using probability of A intersection B equals to P of A into P of B. Therefore, I have this. Now, after taking probability of V common from these two terms, I can write 1 minus probability of A minus of probability of B into 1 minus of probability of A. Now I am taking 1 minus, now by after factorization I will get 1 minus P of A into 1 minus P of B, which is equivalent to probability of A bar into probability of B bar. Hence, we came to the conclusion that probability of A bar intersection B bar is equal to probability of A bar into probability of B bar. Now, using this result, we have probability of A bar given B bar is equal to probability of A bar intersection B bar upon probability of B bar is equal to probability of A bar into probability of B bar, probability of B bar is equals to probability of A bar. Now, from the first part we came to the conclusion that probability of A given B is equals to probability of A. Now on adding second and third, we get probability of A bar given B plus probability of A bar given B bar is equals to probability of A plus probability of A bar, which is always equal to 1. Hence, proved. Thank you very much for watching this video.